Our moon should not exist. I do not mean that as a figure of speech. I mean that if you take what we know about how planets form and you apply it to Earth, you do not get a moon like ours. You get something smaller, or something captured, or nothing at all. What we have instead is a body so large, so close, and so isotopically identical to Earth that for 50 years it has been the single hardest object in the solar system to explain. Here is the number that startled the isotope geochemists when they first measured it precisely. The oxygen isotope ratios of lunar rocks differ from terrestrial mantle rocks by less than 5 parts per million. For comparison, Mars differs from Earth by about 320 parts per million. Vesta, the second largest asteroid, differs by about 240. Every other body we have ever sampled has a distinct chemical fingerprint at the parts per thousand or parts per hundred level. The Moon's fingerprint and Earth's fingerprint are, within current measurement precision, the same fingerprint. That is not what a moon is supposed to look like. A moon is supposed to be a separate world that orbits another world. Ours is not. Ours is a piece of our own world, thrown into the sky 4.5 billion years ago in a catastrophe so violent that it nearly destroyed Earth, and that has been receding from us slowly ever since. In this video, I want to convince you of 3 things. First, that our moon is genuinely anomalous. Not just large, not just close, but anomalous in a way that requires a specific kind of explanation that does not apply to any other moon in the solar system. Second, that the explanation we have arrived at, a giant impact between the proto-Earth and a Mars-sized body we call Theia, is the only mechanism that fits all the evidence, but that the event itself sits inside a narrow window of parameters that did not repeat anywhere else in the inner solar system. And third, that this accident may be part of why we are here. Not in a mystical sense, in a mechanical, measurable sense. The moon has shaped Earth's rotation, stabilized its tilt, mixed its oceans, and possibly even contributed to the structure of its core. Without it, Earth would still be a planet. But it would not be this planet. This will take some time to walk through. It is worth it. The solar system contains, as of the most recent counts, several hundred known moons. The exact number rises every year as surveys of the outer planets continue. Saturn and Jupiter together account for the majority, with hundreds of small, irregular satellites in distant, inclined, often retrograde orbits. The inner solar system is much sparser. Mercury and Venus have no moons at all. Mars has 2 small ones, and Earth has the strange one. Moons in the solar system fall broadly into 3 categories. The first category is co-formed moons. These are moons that condensed out of the same disk of gas and dust that formed their host planet. The Galilean moons of Jupiter, Io, Europa, Ganymede, Callisto, are the canonical example. They orbit in a neat, prograde equatorial plane. They formed in a miniature accretion disk around the young Jupiter, in the same way that the planets themselves formed in the disk around the young Sun. Saturn's major moons formed similarly. So did Uranus's and Neptune's largest companions, with some complications. The second category is captured moons. These are bodies that formed elsewhere in the solar system and were later gravitationally pulled into orbit by a passing planet. Captured moons tend to be small, irregularly shaped, and in eccentric or inclined orbits. Most of Jupiter's outer satellites are captured asteroids. Triton, Neptune's largest moon, is a captured Kuiper Belt object. We know because it orbits Neptune backwards, which a co-formed moon would not. Phobos and Deimos at Mars may be captures, though their origin is still debated. The third category is impact-formed moons. These are moons produced when a planet is struck by a smaller body and ejects debris that coalesces into orbit. This category is, as a matter of empirical record, very small. The Pluto-Charon system is one example. Our moon is the other. There is, in other words, a standard menu: co-formation, capture, or impact. Every moon we know of belongs to one of these three categories. Our moon belongs to the third. But within the third, it is alone in its environment. Pluto is a dwarf planet in the Kuiper belt. Earth is a major planet in Sagittarius, the inner solar system. The conditions that produced Charon do not apply here. The event that produced our moon was, by every measure we have, a one-off. This is the comparison we need to keep in mind for the rest of the video. When I say our moon does not fit, I do not mean it violates physics. I mean it does not fit any of the categories that almost every other moon belongs to. It is its own category with one member. There are three observations that, taken together, rule out almost every conventional explanation for the moon's existence. I want to walk through them in order because each one is stranger than the last. It is too big. The moon is about 1.2% of Earth's mass. That is an enormous number in the context of planetary moons. For comparison, Jupiter's largest moon, Ganymede, is about 0.008% of Jupiter's mass. Saturn's largest moon, Titan, is about 0.024% of Saturn's mass. The two Martian moons together are less than a billionth of Mars's mass. The moon, relative to Earth, is roughly 50 to 150 times larger than these proportional ratios would predict. A co-formed moon should not be this big. The standard models of moon formation around a planet, the disk accretion models that produce the Galilean satellites, do not produce moons that are 1% of the host's mass. They produce moons that are 0.01% of the host's mass, or smaller. To produce a moon-sized moon by co-formation, you would need a disk around the proto-Earth roughly 100 times more massive than any standard model allows. This is the first thing that does not fit. It is in the wrong orbit. The moon orbits Earth in a plane that is tilted about 5 degrees from Earth's orbital plane around the Sun, the ecliptic. It is not aligned with Earth's equator. It is aligned with Earth's orbit. This is the wrong orbital geometry for a co-formed moon. A moon that forms in a disk around its host planet should orbit in the plane of that host's equator, because the disk is set up by the host's rotation. The Galilean moons orbit very close to Jupiter's equatorial plane. Saturn's major moons orbit very close to Saturn's equatorial plane. Ours does not. It is also the wrong geometry for a capture. Captured moons tend to have eccentric, highly inclined, or retrograde orbits because they bring the orbital parameters of their original location with them. Triton orbits Neptune backwards because it came from somewhere else. The moon's orbit is too circular, too close to the ecliptic, and too prograde to look like a capture. The moon orbits as though something set the geometry of its orbit independent of Earth's rotation and independent of any external origin, as though the orbit was determined by the event that produced the moon, rather than by Earth's pre-existing structure. This is the second thing that does not fit. It is made of us. This is the strangest one. And it is the one that took us the longest to figure out, because we could not do it until we had moon rocks in a laboratory on Earth. Between 1969 and 1972, the Apollo missions returned about 382 kilograms of lunar samples. The Soviet Luna missions returned a small additional amount. The Chinese Chang'e 5 and Chang'e 6 missions in 2020 and 2024 returned samples from regions Apollo never reached. We now have lunar material from multiple sites on both the near side and the far side, and from a range of geological terrains. These samples have been measured to a precision that the original Apollo geologists could not have imagined. And the result of those measurements is the single most informative fact we have about the moon's origin. Every body in the solar system has a distinctive isotopic fingerprint, different ratios of oxygen 17 to oxygen 18 to oxygen 16, of titanium 50 to titanium 47, of chromium 53 to chromium 52. These ratios are set during the formation of the body, depending on where in the protoplanetary disk it formed and what raw material it accreted from. Mars rocks look like Mars. Vesta rocks look like Vesta. Asteroid samples look like asteroids. Each body has its own fingerprint. Lunar rocks do not have their own fingerprint. They have Earth's fingerprint. The oxygen isotope ratios match Earth's mantle to within about 5 parts per million. The titanium isotope ratios match. The chromium isotope ratios match. The tungsten isotope anomalies, which are sensitive to when and how the body's core separated from its mantle, match. By every isotopic measure we have applied, the moon is made of the same material as Earth. This is not what a captured body looks like. A captured body would carry the isotopic signature of wherever it formed, which would almost certainly not be the same as Earth's. This is not what a co-formed body looks like either, because the co-formation models cannot produce a body this large in this orbit, and it is not, at first glance, what an impact-formed body should look like. The original 1970s impact models predicted that the moon should be made mostly of the impactor of Theia, with only a small fraction of Earth material. If Theia formed somewhere else in the inner solar system, the moon should have a distinctly non-Earth isotopic signature. Instead, we found a moon that is isotopically identical to Earth. This is what the field came to call the isotopic crisis, and it is the reason the original giant impact theory has been substantially rewritten over the past 15 years. There are 3 live solutions, and the current picture is some combination of all 3. First, Theia may have formed in the same orbital neighborhood as Earth, sharing the same isotopic reservoir. Recent work by Mastrobuono, Battisti, Perez, and Raymond has shown this is more plausible than was previously thought. Bodies forming in similar orbits often inherit similar compositions. Second, the impact may have been so energetic that Earth and Theia were thoroughly homogenized in the debris before the moon condensed. This is the synestia model, which I will return to in the next section. Third, a fast-spinning early Earth combined with a more energetic impact may have produced a moon made primarily of Earth material rather than Theia material. The point is that giant impact is not a single theory. It is a family of theories, and we are still narrowing it down. But the underlying observation that the moon is isotopically a piece of Earth is the strongest constraint we have on what happened. Any theory of the moon's origin has to explain why our companion is made of us. That is the third thing that does not fit, and it is the thing that more than anything else tells us what the moon actually is. The leading explanation for everything I have just described is called the giant impact hypothesis. It was first proposed in the mid-1970s by William Hartman and Donald Davis, and independently by Alistair Cameron and William Ward. It has been refined, challenged, modified, and refined again over the past 50 years. It is now the consensus view, though, as I've said, the details are still in motion. The hypothesis is this. About 4.5 billion years ago, when Earth was nearly fully formed but still in the final stages of its accretion, it was struck by another planetary body. This impactor, Theia, named for the Greek Titan who was the mother of the moon, was roughly the size of Mars, about a tenth of Earth's mass. It struck Earth at a glancing angle, at a velocity of several kilometers per second. The collision was not a clean merger and not a clean separation. It was something in between. The energy released was extraordinary. The outer layers of both Earth and Theia were vaporized. Earth's mantle was partially melted. Theia's core, dense iron and nickel, sank inward and merged with Earth's core. The remaining debris, a mixture of mantle material from both bodies, much of it in the form of vapor and molten rock, was thrown into orbit around the post-impact Earth. This is where the story gets strange in a way that has only become clear in the past decade. I want to pause here because the next part is the part I find genuinely strange. For most of the history of the giant impact hypothesis, the picture was that the debris formed a disk around Earth, analogous to Saturn's rings, but hotter and more massive, and that the moon slowly condensed out of this disk over thousands of years. This is the picture you will find in most textbooks. It is not wrong exactly. But it is no longer the only picture. In 2017, Simon Locke and Sarah Stewart proposed that the post-impact configuration of Earth may not have been a planet with a disk at all. It may have been something they called a synestia, a rapidly rotating, vaporized donut-shaped structure of molten and gaseous rock, hundreds of times larger than present-day Earth, with no clear boundary between planet and disk. The moon in this picture did not form in orbit around Earth. It condensed inside Earth's atmosphere when Earth was effectively the size of the moon's current orbit. This explains the isotopic identity. If Earth and the moon were inside the same vaporized cloud, mixing freely at thousands of degrees Kelvin, of course they ended up with the same composition. They were not separate bodies during the formation. They were the same body. There is a further wrinkle that has changed the picture again in the past few years. In 2022, a team using the Frontier supercomputer ran the highest resolution giant impact simulations ever performed, hundreds of millions of particles, where previous work used millions. The result reported by Jacob Kegereis and colleagues was that the moon could have formed in a single orbit after the impact, not over thousands of years, not even over days. The simulations show a moon-sized body emerging from the debris within hours of the collision, already in a stable orbit while Earth was still glowing from the impact heat. If this picture is right, the moon is not the slow product of a cooling disk. It is a near instantaneous fragment of the collision itself. There is one further constraint on the timing that comes from an unexpected source. The moon's mantle contains samples of material that crystallized from a global magma ocean shortly after formation. By measuring the radioactive decay products in these samples, particularly the hafnium-tungsten system, we can date when the moon's core separated from its mantle. The answer from multiple independent samples converges on roughly 4.51 billion years ago, with an uncertainty of about 10 million years. This dates the moon's formation to within the first 60 million years of the solar system's existence. It also dates the giant impact itself, because the impact and the moon's formation are effectively the same event. This is what the modern picture looks like. A late glancing collision between two roughly Earth formation bodies dated to about 4.51 billion years ago that produced a vaporized cloud rather than a clean disk, and from which the moon condensed in hours rather than millennia, isotopically identical to Earth because it was made from the same well-mixed material. It is a much more violent picture than the textbook version. It is also a much more specific picture with much narrower parameters. And those narrow parameters are what makes the moon hard to reproduce. The impactor had to be roughly the right size, Mars-sized, not Mercury-sized, and not Venus-sized. It had to strike at roughly the right angle, too direct, and the bodies would have merged completely. Too oblique, and Theia would have escaped. It had to strike at roughly the right speed. Too slow, and there would not be enough debris. Too fast, and the debris would have escaped Earth's gravity. And it had to happen at roughly the right time, late enough in Earth's formation that Earth had a differentiated mantle and core, early enough that the inner solar system still contained Mars-sized planetary embryos to do the impacting. These conditions all held simultaneously exactly once. Before we talk about what the moon does for Earth today, I want to say one thing about what the moon has done for us as a record. Earth's surface is geologically active. Plate tectonics, weathering, and erosion erase the surface on timescales of hundreds of millions of years. The oldest rocks on Earth's surface are about 4 billion years old, and they are rare and heavily altered. Most of Earth's earliest history, the period when life originated, when the atmosphere formed, when the first oceans appeared, has been erased from the rock record. What we know of those eras, we know mostly by inference. The moon has no plate tectonics, no atmosphere, no weather, and very little geological activity. Its surface is, in geological terms, frozen. The craters on the moon record impacts going back more than 4 billion years. The Apollo samples include rocks that crystallize within the first 100 million years of the solar system. The Chang'e 6 samples returned from the far side in 2024 include material from one of the largest and oldest impact basins in the solar system. The moon is the only place in the inner solar system where we can directly sample the conditions of the early solar system, because everywhere else that record has been destroyed. This is why every planetary scientist who works on early Earth eventually works on the moon. The moon is not just our companion, it is our archive. Without it, we would know substantially less than we do about how Earth itself began. The moon is not decorative. It is not a passive object in Earth's sky. It is a working part of the Earth system, and it has been doing measurable work for 4.5 billion years. I want to walk through what it does, because the cumulative effect is larger than people generally realize. It stabilizes Earth's tilt. Earth's axis of rotation is tilted about 23.4 degrees from the perpendicular to its orbital plane. This tilt is what produces the seasons. It has remained over the past several million years within a narrow range, varying by only about 1.3 degrees over a roughly 41,000-year cycle. This is, by planetary standards, exceptional stability. The reason is the moon. The moon's gravitational influence on Earth is large enough to dampen the chaotic variations that would otherwise affect Earth's axial tilt. Without the moon, the relevant calculations, first done in detail by Jacques Lascar and colleagues in 1993, and refined since by Lissauer and others, suggest that Earth's tilt could vary chaotically over a range of perhaps 10 to 50 degrees over geological timescales. The exact range is contested. The fact of significant chaotic variation is not. I think the strong form of the rare Earth argument, that without the moon, Earth would be uninhabitable, is overstated. It rests on too many uncertain inferences from a single example, ours. But the underlying observation is solid. Our moon does specific, measurable things for our planet's long-term climate, and we can verify that planets without large, stabilizing moons experience exactly the chaotic obliquity behavior the calculations predict. The strongest empirical support comes from Mars. Detailed climate modeling shows that Mars's axial tilt has varied between roughly 0 and 60 degrees over the past 10 million years alone, and may have reached even higher values earlier in its history. The geological consequences are visible from orbit. Mars has layered polar deposits that record cycles of ice advance and retreat, ancient river valleys at latitudes where water cannot exist today, and equatorial glacial features that point to periods when the planet's tilt was so extreme that the equator was colder than the poles. Mars is what an Earth without a moon might look like over a billion-year timescale. Not lifeless necessarily, but climatically unstable in ways that would make the persistence of complex ecosystems difficult. It slows Earth's rotation. When the moon formed, Earth was rotating much faster than it does now. Estimates vary, but the post-impact Earth probably had a day of about 5 to 6 hours. Over the past 4.5 billion years, the gravitational interaction between Earth and the moon has been transferring angular momentum from Earth's rotation to the moon's orbit. Earth has been slowing down. The moon has been receding. We can measure the present-day rate directly. Laser retroreflectors left on the lunar surface by the Apollo astronauts allow us to measure the Earth-Moon distance to within a few centimeters. The moon is moving away from Earth at about 3.8 centimeters per year. Earth's day is lengthening at about 1.7 milliseconds per century. These numbers sound small. Integrated over billions of years, they are not. A faster rotating Earth has stronger winds, more violent weather, and a different ocean circulation. The moon has, over geological time, calmed Earth down. It drives the tides. The sun produces about 45% of the gravitational tidal force on Earth. The moon produces the other 55%. Without the moon, Earth would still have tides, but they would be smaller and simpler. Solar tides only on a 12-hour cycle with no spring/neap variation. The biological consequences of this are difficult to fully assess because we have no comparison case. But the tidal zones, the periodically flooded coastal regions where ocean meets land, are some of the most biologically productive and evolutionarily significant environments on Earth. They are the regions where some of the earliest transitions from sea to land are thought to have occurred. Without the moon, those zones would still exist, but they would be narrower and less dynamic. It may have shaped Earth's core. There is one more thing the impact may have done for Earth, and it is the most speculative item on this list, but worth mentioning because the recent evidence has gotten stronger. Earth has an unusually large iron core for its size, about 30% of its mass. Earth has plate tectonics, which is not standard for terrestrial planets and may be unique to Earth in our solar system. Earth has a strong, persistent magnetic field generated by convection in its liquid outer core. All three of these facts may be connected to the giant impact. The current best models suggest that Thea's iron core sank into Earth's core during the impact, adding to its mass. The impact deposited an enormous amount of heat into Earth's interior, possibly enough to alter the long-term thermal evolution of the mantle in ways that affected the development of plate tectonics. And a hotter, more energetic core may sustain a stronger magnetic field for longer than a smaller core would. If these connections hold up, and they are still being investigated, then the giant impact did not just give Earth a moon. It gave Earth a larger core, a more dynamic mantle, and a stronger magnetic shield. The same event may be responsible for several of the features that distinguish Earth from its terrestrial siblings. This is the part of the story that most surprises me, and I want to be careful with it. The connections are not proven. They are plausible. They are being actively worked on. But if even one of them turns out to be right, then the moon's importance to Earth is larger than the moon itself. I want to come back to the comparison I started with. If our moon is this anomalous, what does the rest of the solar system look like by comparison? The other terrestrial planets have either no moons, Mercury, Venus, or tiny ones, Mars. Phobos and Deimos at Mars are each less than a billionth of Mars's mass. They are probably captured asteroids, though the question is not fully settled. The upcoming Japanese MMX mission, scheduled for launch later this decade, is designed to bring back samples from Phobos and may resolve the origin question definitively. The gas giants have many moons, but their moons are produced by a different process. Jupiter's Galilean satellites condensed out of a circumplanetary disk, in roughly the way the planets themselves condensed out of the Sun's protoplanetary disk. Saturn's major moons formed similarly. These are co-formed systems. They are large compared to small moons, but they are not large compared to their hosts. Ganymede is the largest moon in the solar system by absolute size, but it is less than 1/10,000th of Jupiter's mass. The only system that resembles ours in any meaningful sense is Pluto-Charon. Charon is worth lingering on because the comparison is closer than most people realize, and the breakdown is more informative than most people notice. Charon is about 12% of Pluto's mass. Our moon is about 1.2% of Earth's. Charon orbits Pluto so closely that the two are tidally locked to each other, both showing the same face perpetually to the other. Our moon shows only one face to Earth, but Earth still rotates freely. Charon almost certainly formed from an impact in the Kuiper Belt, in roughly the same way our moon formed from an impact in the inner solar system. New Horizons data from 2015 confirmed that Charon's surface is geologically distinct from Pluto's, which means the impact mixed material less thoroughly than ours did, possibly because the Kuiper Belt is colder and the impact debris condensed before homogenizing. Here is where the analogy breaks. Pluto sits in a region of the solar system populated by tens of thousands of similar-sized icy bodies. Collisions between Pluto-sized objects, while rare, are a recurring feature of the Kuiper Belt's history. We know of at least one other large Kuiper Belt binary, Orcus Vanth, that probably formed the same way, and possibly more. Earth, by contrast, sits in a region where the population of Mars-sized impactors is now exactly zero and has been zero for over 4 billion years. The accident that produced our moon happened during a 100 million year window at the very beginning of solar system history. After that window closed, the inner solar system became too clean for it to happen again. What our moon required was an accident. What Charon required was a neighborhood. This is what I mean by the strange one. There are moons in the solar system. There are large moons in the solar system. There are even impact-formed moons in the solar system. But there is, as far as we have been able to determine, exactly one moon in the solar system that is this large, this close, this isotopically identical, and this isolated in its environment. That is what we are looking at when we look up at night. The honest answer is that we do not know. We have, as of 2026, confirmed thousands of exoplanets and detected candidates for tens of thousands more. We have not, in any equivalent sense, confirmed a single exomoon. There are candidates. The strongest, identified by David Kipping and Alex Tichy, is a possible Neptune-sized moon around the Jupiter-sized planet Kepler 1625b. A second candidate, Kepler 1708bi, was announced by the same group in 2022. Both remain unconfirmed. The signals are at the edge of what current instruments can detect, and follow-up observations have not been conclusive. There is a specific reason moon-like moons are hard to detect, and it tells us something about the limits of current astronomy. The transit method, watching a planet pass in front of its star and measuring the tiny dip in starlight, is sensitive to the size of the object. A moon would produce a much smaller dip than its host planet, roughly proportional to its area. For a Moon-Earth system at the distance of Kepler's typical targets, the lunar transit signal would be about 7 parts per million of the star's brightness. Kepler's photometric precision was about 30 parts per million for Sun-like stars. The signal we need to see is below the noise floor of the instrument that conducted the largest exoplanet search to date. This is why the confirmed exomoon candidates so far are all enormous. Neptune-sized objects around Jupiter-sized planets. We are not detecting moon analogs because we cannot yet detect moon analogs. The next generation of instruments, Plato, scheduled for launch in 2026, and the proposed Habitable Worlds Observatory, should bring moon-sized exomoons within reach. Until then, our statistical sample of moon-like moons in the universe is exactly 1. This is the part of the story where I want to be most careful about what I claim. It is possible that moon-forming impacts are common, and that most Earth-like planets in the galaxy have something like our moon. The conditions that produced ours, a late glancing collision with a Mars-sized body, may be a generic outcome of terrestrial planet formation, and we just have not detected the moons yet because our instruments are not sensitive enough. It is also possible that our moon is genuinely rare. The narrow parameter window I described earlier, the right size, angle, speed, and timing, may not close often. Many Earth-like planets may have small moons or no moons, or large moons in the wrong orbits. We do not know. The honest answer in 2026 is that we have one example. We have one data point. We have a theoretical framework that explains the data point. And we have reasons to think the framework generalizes, and we have other reasons to think it might not. The rare Earth argument in its strong form claims that the moon is one of several features that make complex life cosmically uncommon. I do not think the evidence supports the strong form, but the underlying observation that we have not yet found anything like our system, and that our instruments would have struggled to find it even if it were there, is correct and worth holding in mind. We may know much more within a decade. Plato will improve our exomoon sensitivity by an order of magnitude. Continued analysis of the Kepler and TESS archives will sharpen the candidates we already have. And the next generation of large ground-based telescopes, the extremely large telescope, the 30-meter telescope, if it is built, may allow direct imaging of large moons around nearby exoplanets. But as of today, the answer to how rare is our moon is, we do not yet have the instruments to know. I want to come back to where I started. Our moon should not exist. By every standard model of how moons form, by every category we use to classify the moons we have observed, by every comparison we can draw with other planetary systems, the moon is anomalous. It is too large for co-formation. It is in the wrong orbit for capture. It is too isotopically identical to Earth to be made of anything but Earth itself. The only explanation that fits the evidence is the one I have spent most of this video describing. A late glancing collision between proto-Earth and a Mars-sized body 4.51 billion years ago that vaporized both bodies into a single rotating cloud, mixed their material thoroughly, and condensed the moon out of that cloud within hours. A specific, violent, narrowly constrained event that, as far as we can tell, did not happen anywhere else in the inner solar system, and the consequences of that event are not confined to the night sky. The moon stabilizes Earth's axial tilt, on which our climate depends. The moon drives the tides, which shape our coastal biology. The moon has slowed Earth's rotation from a 6-hour day to a 24-hour day. The impact that created the moon may have shaped Earth's core, contributed to plate tectonics, and helped produce the magnetic field that protects our atmosphere from the solar wind. The moon preserves a geological record of the early solar system that Earth itself has long since erased. The accident that produced our companion may also have produced several of the features that distinguish our planet from its siblings. We do not yet know how rare this is in the universe. We do not yet have the instruments to find out. We have one example, and we are the example. When you look up at the moon, you are looking at the largest piece of Earth that is not still part of Earth. You are looking at something that was thrown into the sky by a catastrophe that has been receding from us slowly ever since, and that has, in its receding, helped make the planet beneath your feet the kind of planet on which a person can stand and look up at the moon. Our moon is a part of us. It always was.